A 1.43 kilogram block is initially at rest on a frictionless inclined plane. The angle between the surface of the ramp and the vertical side is 65 degrees. Determine A, the acceleration of the block as it slides down the inclined plane, B, the magnitude of the normal force, and C, what is the final velocity of the block once it moves 2.87 meters down the inclined plane. So first we can identify our mass as the quantity with units of kilograms. Next, they specify that the block is initially at rest, so that might be important. Initial velocity is 0. It's frictionless, so lowercase f is 0. They identified the angle, which I labeled as phi. They said this was 65 degrees. And we could work with this, but we can use this angle to identify what we're normally given, the angle at the base of the ramp, which I'll label theta. Since the sum of all angles inside a right triangle, or any triangle, should be 180 degrees, we could take 180 degrees, subtract away the right angle, subtract away the given angle phi, and we'll get that remaining base angle. So theta must be 25 degrees. Finally, they give us a distance x is 2.87 meters. So let's find the acceleration, the normal force, and everything else. Well, first off, we can still graph some forces acting on the block, even though there's not many. There's a normal force. Again, normally there's a force pressing the block up the ramp. Normally there's friction, but those don't exist in this problem. But there is gravity still. So I'll graph the force due to gravity, or the weight, W. And this should be broken apart into two components. The amount of weight in the vertical direction, Wy, and the weight in the x direction, which is Wx. Now, there's an angle inside this triangle that we just formed between the gravity and its components, and that's the angle theta. Perfect. So the setup is complete. Notice that they specified the block is moving down the ramp, so motion occurs to the left. So if there was a friction force, in this case, friction would actually act to the right. So the only force responsible for pulling the block down the ramp would be Wx. So let's see what happens. So if you were to apply Newton's second law in the x direction, sum of all forces acting in x, well, there's only one force acting in x. That's Wx equals ma. Now, the formula for Wx is mg sine theta equals to ma. Notice that m appears on both sides, so we could divide both sides by m. They cancel out. So the acceleration is negative g sine theta. Perfect. So let's find out that value for acceleration. That's part A. Once you plug in those numbers, we'll get negative g, which is 9.81, sine of 25 degrees So for the acceleration, we'll get negative 4.15 meters per second squared. And as we mentioned before, acceleration is ambiguous. The sign has two possible meanings or interpretations. Well, a negative acceleration could indicate that the object is moving left, which it is, or a negative acceleration can indicate a deceleration. The object is slowing down. But anyways, part B was, what is the normal force? So how hard is the surface pressing against the block? Well, that's a vertical force, so you'd apply Newton's second law in the vertical direction. Now the block is not lifted vertically off the ramp. No motion occurs in the y direction or along the y-axis. So the acceleration is 0. All forces acting vertically, well, that would be a normal force in green and the Wy. So we have a normal force acting up, Wy down. So notice that if you add Wy to both sides, yeah, we see that normal force is equal in magnitude to Wy. And Wy is mg cosine theta. So in this case, this is the expression for the normal force. Normal force equals the mass, that was 1.43. Acceleration due to gravity, that's 9.81. And then cosine, 25. So normal force equals 12.7 newtons. And good, notice this equation we got here, or rather, we obtained n is equal in magnitude to Wy. You could just look at the diagram and infer that as well and say, oh, according to Newton's third law, I see that n and Wy are equal and opposite. But I don't like that because then it seems like magic math. So if you perform Newton's second law, you arrive to that conclusion anyways, and you see Newton's third law, that if the ramp is pressing against the block, then the block is pressing back against the ramp. But anyways, let's just finally find part C, which is more of a kinematics question. It asks, find final velocity, which is Vf. So we use kinematic equations, and this is where the distance x comes into play, which was 2.87. So what's a kinematic equation that contains x? Well, one that comes to mind is v final squared equals v initial squared plus 2ax. The block starts from rest. If I square root both sides, I obtain this expression. Now, whenever you square root both sides, technically you tack on a little plus or minus. Because remember, the block actually moves to the left. So we're going to use the negative in this case. So again, this is going to be negative square root 2a, which is negative 4.15, And then x was given to us as 2.87 meters. Oh, and this is down, so we can interpret that as a negative 2.87. So that way we get the square root of a positive number. So finally, after you take the square root, well, first off, that product is 23.8. So yeah, you're going to take the square root of 23.8 and then multiply by -1. So for your final answer, you get about negative 4.88 meters per second. And that's how you'd find the velocity.